Okay, everyone, let me give me a few minutes to get some announcements out and to go over the last two quizzes. So this Thursday is our last class, but I'll be traveling starting tomorrow, so I won't be here on Thursday. If you need help, you can, Alex and Soyash can help you with the lab. Okay. The final exam will be given like the midterm was on Blackboard, multiple choice. You can take it whenever you want during finals week. So that'll be available from next Wednesday to the following Wednesday. So April 30th to May 7th. And it's comprehensive and 25 questions, 2 hours. Okay, just log on whenever you can. Obviously, you should take it by yourself, not collaborate with other people. It's to be treated like an exam, okay? The exam will cover the material from both parts of the course. So it'll have the bit twiddling and interfacing material on it, as well as the real-time systems and control theory. So we had two quizzes. So I'm going to just go over those real quick because the final exam questions will be very similar to these. So for the control theory quiz, we had a question: which of the following is a LTI, linear time invariant system? The answer is this one, right? Because it's linear because it only has constant coefficients multiplied against state variables or derivatives of state variables or integrals of state variables. So this one's nonlinear because it's a ratio of two state variables. This one's nonlinear because it's the product of two state variables. This one is also nonlinear because it has a state variable squared. Right, make sense? What's the S domain form of this time domain expression? So it's a derivative of the G state variable. So derivative means you just multiply it by S, right, in the Laplace domain. Okay? And if it were an integral, then you would divide by S or multiply by S to the negative first power, for instance, if it was the first integral. Which of the following is a method for determining if an LTI system is stable? These are all just mostly made up. The right answer is you want to check if the impulse response of the transfer function is bounded. Because remember, the impulse contains an infinite number of frequencies, right? So the reason why people use the impulse response is that you could have a system that's not bounded or that's not stable for some frequencies, but it is stable for others. Right? So if you put an impulse in there, you're covering, every possible input frequency, right? So if it's stable when you hit it with an impulse, that means it will be stable for any input, which means it's bounded input, bounded output, stable. Now stability is, I mentioned that, stability basically, in reality, you're not going to have a system that's exploding infinitely, right? Because that would take an infinite amount of energy to do that. But the goal is when you have a stable system, you want it to converge on a certain value. Set point. All right, what are the following are valid eigenfunctions for the transfer function 1 over s squared minus s minus 56? So for this, you have to get this into a form where you can calculate the eigenfunctions. So basically, you just factor the denominator into s minus 8 times s plus 7, right? You guys remember how to do that, right? And then you have to split it into a over s minus 8 plus b over s minus 7. So you have to solve for a and b, which is a little tenuous because there's two unknowns in one equation. But you can kind of fake it by coming up with a common denominator, right? And adjusting the numerators appropriately. And then You can deliberately set S to be a value that, knocks out A or B, right? And then you reduce it to one equation, one unknown. So anyway, B is 1 over negative 1/15th and A is 1/15th. And then you have it into a form, then you can do the inverse Laplace transform, which are just those two exponential functions, right? Any questions? Okay, what's the transfer function resulting from feeding the function 1 over s plus 1 into the function s over s squared? I don't know if that's the right way to state that, but what I'm asking you there to do is to convolve those two S domain functions, meaning, you just multiply them together. So yeah, that's it. That's basically it, and then you can reduce it. Okay, this is a question that asks you to design a cyber-physical system to counteract the movement of a regular pendulum. So this is like basically dampening a pendulum. Like if you have a pendulum, you try to swing it, it's going to stop it, right? That would be a cool project, right? Just hanging a pendulum with some kind of actuator at the top, and then you whack it, and it goes to start swinging and then stops, right? So you need to model the physical system. And so I chose this because a pendulum is a fairly easy system to model, at least a single pendulum. Once you get into double pendulums, then it becomes crazy. So the question, though, is what's the inputs and outputs? Well, the input, so again, I'm just modeling the physical system, not the controller, right? This is just a physical model, which should be modeled in the S domain because it's a continuous system. And so before I can marry a controller to it, I need to have a physical system model. So the output is the angle, right? That's what we're trying to control. That's like our process variable is the angle, right? And then there's a force input, which is the manipulated variable. That's the input into the system. So the idea is that I can apply an external force that's like a torque, right? That's the F. So the time domain equation is F plus second derivative of the angle equals minus B over M. M is the mass and B is the friction of the pendulum. Multiplied by the first derivative of the angle minus G over L. G is a gravitational constant. L is the length of the pendulum. Multiplied by the angle. So this is, I just pulled that. That's just the pendulum equation. You get different versions of that depending on how realistically you want to model it. In this case, I chose the version that has the damping factor B, the friction, because that one, if you swing the pendulum, it'll eventually stop swinging, right? It'll dampen. There are some simplified versions of this that will, just swing forever because there's no damping. Okay, so what's the S domain transfer? So all that is to basically say you just want to do the S domain. That's a really complicated, long question, but really what I'm asking is just do the S domain transformation. So I basically did that, and then you have to simplify it essentially. And then the transfer function. Remember, the transfer function requires that you have the output. You express it where it's a ratio of output to input, right? So in this case, remember the output is F, the input is theta, the angle. The output is F, the input is theta, right? Is that right? Yeah, right. No, sorry, the input is F, the output is theta. Sorry, I said that wrong, right? Because I'm applying a force and I'm trying to stop it from swinging, and this, the angle at which it's swinging is theta, right? Okay, any questions? All right. The reason I asked that, by the way, is because this one had a second derivative. So that one you multiply by S squared, for that one. Okay, what's the S domain transfer function PID controller with KP2, KD1, and KI4? This is trivial because these numbers are just the coefficients multiplied by nothing in the case of proportional control. Derivative is you're multiplying by S, right? And the integral you're multiplying by 1 over s, right? So literally, you're just taking these numbers and multiplying them by those powers of s, 0, 1, and -1, respectively, right? That's it. And then, of course, you can always express it as a ratio of two polynomials. Oh, all right. What's the Tustin transform? So this one, we're going from a S-domain continuous transfer function to a discrete transfer function in the Z-domain. So Tustin goes from S to Z, but remember there's that extra parameter T, time step. That time step, you have to know the time step when you do the conversion from S-domain to Z-domain, right? So how do you do that? You basically just substitute in this wherever you see an S, right? And then, do the algebra. And so you end up with this. So again, you have the F is the output, Y is the input here, right? And of course, you can reconceptualize this as, you could conceptualize it the other way. Remember, a differential equation doesn't really have inputs and outputs, but you apply this depending on how you're applying the transfer function. And then it's just a ratio of two Z-domain polynomials. Okay, so the time, once you do this, by the way, I don't think there's any way to go back and extract what the time step is from this. So once you put that time step in and you compute it, it sort of gets absorbed by the transfer function. So you can't look at that and figure out that you used a time step of 1, or at least not in a straightforward way. Okay, what's the closed loop transfer function of the system below? This is just plugging numbers in. So remember that the closed loop transfer function is the open loop divided by 1 plus open loop. What's the open loop? Well, the open loop is just the convolution of these three transfer functions, so it would just be f times g times h. So you just substitute f, g, h, or f times g times h into where I have OL there, and that's the answer. Simple. See, and they said this class was hard? Control theory? Really? Okay. Seems pretty easy to me. Okay, so what's the discrete time domain implementation of the transfer function? Now this is the one I think this is cool. So you have a transfer function here in the Z domain, but how do you put this in the time domain? Right? So like with the Laplace, to go from Laplace to time domain, very difficult. But with Z-domain, it's a lot easier. That's a difference between S-domain and Z-domain. The reason is because, remember, the Z-domain maps directly into the time domain, because if you multiply a state variable by z to the negative first power, that translates directly into the time domain. That means whatever that variable was one time step ago. You guys with me? Now, the problem, though, is that you can't do the same thing with a positive coefficient. You can't have, you can't have a positive exponent, not coefficient, exponent. You can't have a positive exponent of z and move that into the time domain, because that would require you that you can tell the future, right? That would require you to be able to see the future. You need like precognition to do that, right? But a negative exponent means the past. So if you multiply z to the negative fourth power times state variable f, that just means what f was 4 time steps ago, right? And in a digital logic circuit, you would just use shift registers to implement that. So a z to the negative 4 is like having a shift register with just 4 cycles of delay, right? Very simple. So in this case, I had to basically ensure I had to manipulate this to make sure I have negative exponents, and then very simple to go to the time domain. Typically with the time domain, use brackets instead of parentheses. I don't know why, it's just a notational thing. I use parentheses. So I had f of t minus 1, that means 1 sample ago. It should have been, I should use brackets there, but you get the idea. Okay, any questions? Okay, so that's that, and then I had another quiz for real time. This was due last week. Okay, so assume you have 4 tasks with execution time period values of 4, 15, 5, 20, 6, 25, 7, 30. What's the utilization? Pretty much just add up the ratios, right? So that's a 99% utilized system, which means it would be difficult to schedule it. What is the RMS bound? Remember, there's multiple RMS bounds, but the one that we covered in this class was where you multiplied the ratios plus 1 together, right? This is, I think, one of the newer RMS bounds. This is still an open problem in computer science. This one gives you a bound. It means that if you're under the bound, you're guaranteed to be able to schedule it. If you exceed the bounds, then maybe not. As long as your utilization is less. If your utilization is over 100%, definitely not. I mean, assuming you have 1 CPU. So if your RMS bound is in between the RMS bound that you calculate and 100% utilization, then you may or may not be able to schedule it. There's no way to know, because even if you simulate it, you're never sure how long it'll take in the simulation to bust a deadline, right? Assuming these are not in harmonic periods, which they typically are. Okay, assume there's 3 tasks with 2 10s, 7 20, 25 40. Are they schedulable? Probably not. I said cannot be scheduled, but it exceeds the bound. The bound is anything that's greater than 2. Not sure. The only way you know that for sure that it can is if the utilization is more than 100%. Which it is. Sorry. So the utilization is 117.5%, just like my grading scale in 611. Okay. All right. Assume 4 tasks, 1, 2, 3, 4, with execution time periods 2, 5, 4, 7, 3, 11, and 4, 12, and 2 processors. Are they schedulable using partitioned RMS scheduling? If so, which task processor assignment is schedulable? So this is partitioning. Remember, the partitioning is when you just have each task associated with a specific processor. That simplifies the problem a bit, although not really, because there's a combinatorial number of ways to do that assignment. So I came up with every possible way of assigning tasks to processor 1 and processor 2. And then for each one of those configurations, you calculate the RMS bound. And you're looking for a case where the RMS bound on both processors is less than or equal to 2. In this case, it's equal to 2 here, and it's equal to 1.07. So it turns out that you can schedule these, but it's not easy, because there's only one possible way to assign these tasks to the processors in which they'll schedule. So task 1.4 is on processor 1, task 2.3 is on processor 2. Any other combination, any other assignment will not meet the RMS bound. Assume you have 3 tasks, 3.10, 4.11, 4.12, under which algorithms are they schedulable? So utilization is 99.7. So only for certain, I can schedule this with EDF. Unclear if it can be scheduled with RMS. And remember, the difference is EDF is you have to continuously recalculate priorities, whereas with RMS you don't. So I don't think there's any practical real-time operating system that uses EDF scheduling. Assume 4 tasks. What is the largest value of n that would make the task schedulable with rate monotonic first fit scheduling? So this is the one where you basically just calculate the bound. So you calculate the utilization, and you check to see if the utilization is less than or equal to 2 times the square root of 2 minus 1, where this 2 is the number of processors, right? So the bound here is 0.82. So if our utilization is less than or equal to 82.84% out of 200, because there's 2 processors, then we can use the RMS first fit algorithm, which is pretty bad that I can only use. That's like less than half the capacity of the system, right? but that's the bound for that algorithm. And then in this case, I have to solve for n because I have an unknown. So n is 5, right? So if that last task is 5 out of 22, then it would schedule. If it's 6 out of 22, then it won't meet the bound, in which case we're not sure if it'll schedule. Assume 4, and by the way, when I say schedule, I mean guarantee that it won't miss a deadline. Assume 4 tasks, 2, 8, 5, 12, 6, 16, and 7, 20. Are they schedulable with EDF on 2 processors? Oh, by the way, remember too that these execution times are worst case execution times. So in practice, your actual execution time may be less, but you have to make guarantees based on the worst case execution time. Okay, and we talked about how to calculate worst case execution time. Usually you calculate it with a certain confidence interval. Because if you run code on any CPU, the execution time is going to vary. It doesn't matter, even if you're running on bare metal like we do in 313. There's still going to be cache misses and interrupts. There's still things that can cause one run, even if the code is control agnostic. There's no if statements, there's no branches. It's still, or there can be branches, but the branches are always, the loops are always behave exactly the same way regardless of the input. Even in that case, you're going to have some variation on the execution time. The only way I know of to build a system with perfectly predictable execution time is in FPGA, which is why you see a lot of references to that, like in Simulink and MATLAB, FPGA deployment. Assume 4 tasks. Are they schedulable with EDF on 2 processors? So this is the weird one where you calculate the utilization and you check to see if that's less than 2, right? Because that's a dead giveaway. If it's, if you don't have enough system capacity, it won't schedule. Then you have to find the greatest common divisor of the periods, and then you multiply the ratio of execution time to period against the greatest common divisor, and you're looking for any that are not integers, any of the products, right? And then if you have any there that are not integers, then it means there's a chance you can't, right? And then how many possible ways can 5 non-periodic tasks be scheduled? The non-periodic tasks. Non-periodic means they just run once and they're done, right? Like every task you run on Linux. 120. Which statement is true? RMS requires dynamic priority. RMS requires static priority. EDF and RMS requires static priority. EDF requires static priority. RMS is static, so that's false. RMS is static, so that's true. This is false, and that's false, so it's B, right? So EDF, again, EDF has evolving priorities. Our RMS doesn't. And again, the RMS priority is just the period. The shorter the period, the higher the priority you have. And then, which statement is true? Any task having a utilization that meets the EDF bound will also meet the RMS bound? No. Any task that can be scheduled on 2 processors can be scheduled on 1? I don't think so, no. Not with the algorithms that we covered anyway. Might be something out there I don't know about. Any task that can be scheduled with EDF can be scheduled with RMS? No. Any task that can be scheduled with RMS can be scheduled with EDF. That's true, yes. Yeah. Because EDF is more powerful in that sense. It's kind of the tasks that you can schedule with EDF is a superset of RMS. Okay, and that's it. Any questions? Okay, so make sure before you take the final, you go back and review the material on interfacing and exceptions and I/O address ranges, programmed I/O, that kind of stuff. And it's an open book, open internet exam, but just take it by yourself. And like I said, that will be the next Wednesday to the following Wednesday. So there's 8 total days span that you can take it. You can take it anytime you want. It's 2 hours. Okay. Meanwhile, the Lab 5, we're a little short, obviously, on that. You only have till reading day, Tuesday, a week from today. I don't think that's totally unreasonable, though, because remember that this lab doesn't require you to do low-level bit twiddling stuff, so you can use the driver for the pulse count, and you're using the real-time operating system free RTOS to do all the handling, all the timing and stuff. So, and you're implementing a control with PID controller. So you'll have to tweak the PID controller manually. That's not a great way to do it, obviously, but in this class we'll just use trial and error for that. And then it's just a matter of figuring out what your time steps. How often do you want to sample the P count? How often do you want to update the motor speed, right? And that's basically it. If you don't get everything done, we'll have partial credit. Obviously, just get as much done as you can, okay? So like I said, just one final reminder, I won't be here on Thursday. And then Thursday will be our last meeting. If you need help, contact Soyash or Alex, and they'll be happy to help you.